So last time we talked about proof by contradiction, and not only did we talk about that, but I'd just like to remind you that at the very end, we basically could summarize our work process when wanting to do a proof into basically having two boxes. This is our to prove box, which is basically whatever we want to prove, and over here is our what we know box. What we know, and I'm just gonna put is true. So this is our resources basically. What we know is true, and we want to find the connection between here and here is what we're trying to do. And what did we say we want to do when we have a situation where we want to prove if P then Q? Then this is the same thing as assuming that P is true, which means we're putting P in this box, we're transferring it in that box, and letting Q stay here. That's what we did in the last video, that's what we explained. So if you need a reminder, please watch the previous video. So we can write this. So whenever we have something, arrow, something, then you should always perform this step. And most importantly, it puts something in your what we know box, which is important. Like you need something to work with in the first place if you want to draw the connection between these two, right? And we also showed that we can have whatever we want in our to prove box. We can assume that it's not true, proof by contradiction here, say not Q, and then our goal to prove now turns into proving a contradiction instead. Contradiction. So these are our two strategies. Either we do it directly without showing a contradiction like this, just instantly draw the connection, or we can assume that Q is not true and see what goes wrong with that. And either way works. Sometimes one is more convenient to use than the other, and yeah, with experience you will know which strategy is more appropriate. Right now we want to look at a different situation here. What if we want to prove that two sets are equal? And this is a very common question. What if we have two sets A and B and we want to show that they're equal? This means that they contain the same exact elements. So if A is 1, 2, then in order for it to be equal to B, B should also contain 1 and 2. That's when two sets are equal. And we talked about this in the set theory video. So if you need a reminder on that, just watch it again. It's always there. We also talked about what this statement is equivalent to. We showed in that video that this statement is equivalent to A being a subset of B and B being a subset of A. So we have to find the proof that this is true and this is true. So we need to find two proofs basically, because we're trying to prove two statements. This is one separate statement and this is another separate statement. Well, that's the exact same thing as separating them into two different lists. So essentially what we can do is we can just separate them down and get rid of this one right here, because it communicates the same information. Like over here, we want to prove this is true and prove this is true. And if we separate them into lists like this, then it communicates the same idea. What do we want to prove? We want to prove that this is true and this is true. So it's the same thing. So this is just a good way to organize, separate things out, break things up into smaller pieces, makes it clear what to do next. Now usually this is fine. We can stop here. Maybe it will be already clear or easy to draw the connection between what we know and what we want to prove. But sometimes it's not that clear and we have to break this down even further. So what do we do then? We've shown also in previous videos that this is equivalent to saying, well, if x is in A, then x should be in B. This logical statement communicates the idea that A is a subset of B. This is how we communicate the idea that A is a subset of B, through logical symbols and statements. On the other hand, well, if it's like this, then we have it, the other way around. So in order to show that A is equal to B, we have to prove two different statements. We have the first statement over here and the second statement over here. So usually when you're reading a textbook or something and they show you a proof that two sets are equal, they'll usually have one paragraph dedicated to the proof of this statement, and they'll have another paragraph dedicated to the proof of this statement right here. So just a heads up if you're, well, wanting to read further into proofs and logic and set theory and whatnot. So yeah, that is the idea. That is what we're supposed to do. We're supposed to handle these proofs separately. So I'm going to bring this down over here, and we're gonna just separate this out. Yeah, so this also, so you should follow this whenever you have two different things to prove, not necessarily of this form. If you have to prove P and if you have to prove Q, then just separate them out and deal with them separately. So like I said, what can we do when we have a statement of the form if P then Q, and we want to prove it? What can we do here? Well, we can assume that x is in A and show that x is in B. So somehow we need to draw the connection between these two. Likewise, at the bottom over here, we can assume that x is in B and find a connection between this guy and this guy. So usually this is as deep as it gets. This is like the problem has already been broken down to the smallest possible. The problem has already been broken down to the smallest possible, atomic. We've deconstructed everything atom by atom, and there's no way to go down even further. So usually at this point it will be very easy to identify the connection between the two. So let's try to do this with an example. Let's say we want to prove that the infinite intersection AI union B is equivalent to this guy right here, right? So if this notation is not clear to you, basically what we mean is this guy over here is A1 intersect A2 intersect A3 ... and then we union that with B. So the infinite intersection of A's combined with B. And on the other side we have A1 union B intersect A2 union B intersect A3 union B, and so on and so forth. We want to show that these two statements are equivalent. So this will be interesting. Let's see what we can do. So as we discussed earlier, this is equivalent to proving two separate statements, right? So it's equivalent to proving if x is in this guy right here, then x should also be in this guy. And then we also have another one that we need to prove, which is just like the converse or the opposite of this statement, right? And what did we say we can do if we have a statement of the form if P then Q? Well, then we can just simply move this over to the other side and also move this guy over to the other side, and let's just move these guys back as well. Alright, so now we have the format that we had earlier. So like I said, we already reached the format that we want, that we need. This is as deep as it goes, and it should already be clear what the connection is between the two. So let's work out what the connection is one by one. I'm going to move this over to the bottom side just so we have more space. Right, so what's the connection? What does it mean when X is in the union of two different sets? How can we represent that in terms of logical statements? Well, if X is in, let's say this is AB, if X is in the union, then what does that mean? It means that, well, X is either in A or it is in B, because X being in the union of the two means that X is somewhere within this cloud over here. And that is equivalent to saying that X is in A or, so that's a V, or X is in B. Right, so let's just write that down. Alright, so this is an important moment here. If we have something of the form P or Q, then we can't separate them into two different lists like this. We can't separate this, put this over here, like we did with the AND. Because like OR and AND, they have very different meanings. OR means that either this is true or this is true, and if you separate them, it would imply that both of these are true, which is not the idea that you want to communicate. Okay, so how do you handle this? Well, I think it's easier if I use a different example to explain. Well, what if we want to prove that a statement P works for the natural numbers? And by natural numbers, I mean numbers 1, 2, 3, and so on and so forth. What do we know about the natural numbers? Well, that's easy. We can say that the natural numbers is the union of the even numbers and the odd numbers. And now what? Well, think about it. If we prove that the statement works for the even numbers, and if we prove that the statement works for the odd numbers, then doesn't these two mean that it works for the natural numbers? Because, yeah, just think about it. If we have a proof that the statement works for the even numbers, then we know it works for the numbers 2, 4, 6, 8, 10, and so forth. And we also find a proof that it works for the odd numbers, say it works for the numbers 1, 3, 5, 7, and so on and so forth. Then what do we have if we combine the two? Then it works for every single number. So this is how we deal with OR statements. And this union over here, well, that's secretly an OR statement, right? Because we just converted this guy into that guy. Basically, the union of the two sets just converted into an OR statement right there. And when we're dealing with an OR statement, we need to find a proof separately for each one. So what does that mean for our case? It means that we have to find a proof for this guy, and we also have to find a proof for this guy. And we have to do it separately. Alright, so let's try to find a proof for this guy, right? So this is what we know. And we need to use this to prove that, right? We'll handle this guy separately later. What does this mean? This means, well, yeah, think about it. What does it mean when X is in the intersection of every single one of these sets? So basically, if we have two sets, for example, A1 and A2, and X is in the intersection of them, that means X is here, right? And if we have A3 and X is in the intersection of A1, A2, and A3, then X is in all three of the sets. And if we have A4, we have something that looks like this, A5, something that looks like that. So what does it mean if it's in the intersection from A1? So what does it mean if it's in the intersection of A1, A2, A3, A4, A5, A6, and so on and so forth? Well, that has to mean that X is in every single one of these sets. So X is in A1, X is in A2, X is in A3, and so on and so forth. But this is an inappropriate way to write it. Instead, we can simplify everything down. Instead of writing it in terms of a list, we can say X is in AI for each I. And by for each I mean for each I equals 1, 2, so on and so forth. What about on the right side? Can we simplify it as well? Let's see. X is in AI union B, and well, in the intersection of all of that. So, well, it's the same thing, isn't it? If it's in the intersection, then X should be in AI union B for each I, right? Cool. So maybe if it's not clear, I'll write it down in a form of a list. So X is in A1 union B, and X is in A2 union B, X is in A3 union B, and the list goes on and on and on. Let me just draw a line between the two to avoid confusion. Separate these two boxes over here. So this is how we write it down in terms of a list. But here's an interesting thing. What do you notice about this list? We can do something about it. We can simplify it even further. We can break it down into smaller pieces. How? Well, this tells us that X is in the union of two different sets. So this is equivalent to saying X is in A1 or X is in B. This is X is in A2 or X is in B. This is equivalent to saying X is in A3 or X is in B, and so on and so forth. So how do we convert this list into just compact English language? So this means that, well, X is in AI for each I, or X is in B, right? We're just converting the list back into English language. So this means that this statement over here that I'm underlining is equivalent to this statement over here. So we can just replace this guy with the other guy. Okay, cool. Let me just do that then. So what do we want to prove? We want to prove this statement right here. And this is an OR statement. So let me just write it down. P or Q. So if we want to prove something that is of the form P or Q, then it suffices to prove only one of them. Because what does this mean? It means prove P or Q. So, hey, you can pick either one. If you find the proof for P, then this is true. If you find the proof for Q, then this is also true, because that's literally what the question is asking for. Prove P or Q. Pick whichever one you want. Alright, so which one should we prove? Should we prove this guy or this guy? Which one do you think is easier? Well, the answer is simple. What do we have? What do we know? Right? We know that this is true. And, these two things, they're exactly the same as one another. So we want to prove that this is true. And we know that this is true. And well, since they're exactly the same as one another, then we are technically done. Alright, but that's just the first part. Remember, we still have to find the proof that it works for... Crap, I erased it. We have to find the proof that it works for this guy as well. So, alright, this guy. Alright. Are we done here? Well, seems like it. Same idea. We want to prove that either this is true or this is true, which means it suffices to find the proof for either one of them. And, well, this is an exact match with this, and we know that this guy is true, which means that this guy is true, which means that we have proved this statement because it's an OR statement and we only need to find a proof for one of them. So if I give a check mark to this guy, then I give the check mark to the whole thing because, well, it's an OR statement. So that's it, we're done. Hey, cool. Alright, let's move to the bottom part now. Let's see. Let's try to simplify everything again. Well, we know how it works already, right? This guy is same as this guy, so we can simplify it into this statement, right? And we know that this guy right here is equivalent to the top left, which means we can write x is in, we're just copying this portion over here, x is in the intersection of this guy and this guy, or x is in B. Okay, cool. And then now what? Well, we can rewrite this portion, right? This is one statement, this is another statement. So we can say, what does this statement mean? Well, we've already talked about it. If x is in the infinite intersection, it means that x is in ai for each I. And we have or x is in B. And, well, what do you know? This guy over here is equivalent to this guy over here, which means we're done. We know that this is true, and we want to prove that this is true. And since they're equal, we are done. So it turns out that we don't really have to do what we did like before, where we found the proof for each one of these separately. But if you want to do it, it's fine as well. We can separate for each one of them. X is in AI for each I. And, well, this leads to a proof of that because, well, this side over here corresponds to this one over here. And if we want to find a proof separately for x is in B, well, then just write that down here. And where's the connection between this guy and this guy? Well, it's right over here. So we know that this is true, which means that x is in B is true. And, well, if you put a tick mark here, you put a tick mark to the entire thing because of the OR statement, so we're done as well. So sometimes you can just skip this entire process because it's blatantly obvious that this is equivalent to this. Sometimes it won't be so obvious though, and basically it's safer if you try to do it separately like this instead. And so, well, since we've done every single thing, we've proved every single thing that we wanted to prove, then we can stop now, and we can safely conclude that this thing over here is a mathematical truth. And just as an extra piece of information, the opposite of this statement, in other words, I'm talking about flipping the intersection with a union. So instead we have the infinite union AI intersect B is equal to union infinite AI union B. If we, oh crap, yeah, intersect B, if we flip the intersection and union around, this still holds true as well. And, well, you can try the proof out yourself if you want to. It's pretty similar to what we did here, so it shouldn't be too difficult. And yeah, these two statements over here are actually very important when it comes to topology, and I'm actually thinking of doing a topology course after I'm finished with this one. So if you're interested in that, stay tuned. Otherwise, that's fine. That's it for today's video. Thanks for watching.